Hi guys, welcome to General Organic and Biochemistry. This is our first week together. This is our first video of the week. Now, this week in particular, we have 3 videos. And what I've done is I've taken the notes really slowly to get them as neat and organized as I can. And then I've kind of sped them up 3 times. So this is a 20-minute lecture, but it took me like 60 minutes to write it out. And when I do that, it adds up to my talking speed. So right now what we want to do is we want to just start off here on page 1 of our notes. So this is the first of 3 videos for this week. And this is my chapter 1, Matter and Life. So first, it looks like we're going to start off with a few definitions that you want to have written down in your notes. Chemistry is the study of matter. So it's the study of matter in all of its nature, its properties and transformations. So what is matter? Well, matter is anything that has mass and takes up space. So another definition of matter then would be anything you can see, taste, touch, or smell. So pretty much everything, right? Different kinds of matter can be further characterized by their changing properties. So there's a little star there and it says different kinds of matter can be further characterized by their changing properties. Properties, or a property of a substance, is a characteristic that's useful for identifying a substance. So when we talk about changing properties, it usually follows suit that we'll talk about things like physical changes and chemical changes. So number 1 right there, a physical change. A physical change is something that does not alter the chemical makeup of a substance. And we'll go through some examples in just a second. Number 2 is a chemical change. Chemical change is a change in the chemical makeup of a substance. Chemical changes are often viewed as chemical reactions. All right, moving on to page 2 of our notes here. So we're at the top of page 2, top of the page, it says, example, of the following, is this a physical change or a chemical change? A metal surface being grinded down. So you're kind of sanding or grinding down on a metal surface. B, fruit ripening. C, wood burning. D, puddle evaporating, like a puddle of water. So A, metal surface being grinded down, this is a physical change. B, fruit ripening, this is a chemical change. A chemical reaction is occurring that's ripening the fruit. Same thing with wood burning, right? We're burning wood to produce water vapor and CO2. And then a puddle evaporating is just a physical change, just evaporating water from the liquid state to a gaseous state. All right, so speaking of states, that moves on to our next topic here. Matter exists in 3 states. So 1, 2, 3. We have a solid. Solids have their own shape and their own volume. So they have a definite shape and a definite volume all their own. Liquids have a definite volume, but they have an indefinite shape. They'll take up whatever the shape the container they're in. Gases have no definite volume, no definite shape. All right, so change of state. Definition of change of state is the conversion of a substance from one state to another. Now, how easily this can be done depends on temperature. All right, so now we're on page 3 of this video's notes. And we're going to be making a little schematic here, like a little flow chart. So the top of the page, it says the classification of matter. So to begin our flow chart, it states that matter is either a pure substance or a mixture. So we're going to separate those two out. We're going to separate matter into pure substances and mixtures. But as an example first, water, H2O, and sugar alone, those are just pure substances. But if I combine the two or stir them together, I get what's known as a mixture. So H2O and sugar alone are pure substances. They're compounds. But stirring some sugar into a glass of water, now I'm making a mixture, specifically a solution. So now let's begin our flow chart. So we have matter at the top, and we ask ourselves a question. Are its properties and chemical composition uniform throughout? Does it have the same composition throughout the entire sample? All right. If the answer is no, then we move over to the left-hand side and we write this down as a mixture. Okay. And then the mixture, we're going to have a little blurb that we want to write underneath our mixture on our flow chart. It says its components can be separated from each other by physical means. So an example of a mixture, and we're going to write some down right now, but its components can be separated from each other by physical means. Now, the top where it says matter, we ask that question, are its properties and chemical composition uniform throughout? If the answer is yes, we have a pure substance on the right. So examples of a mixture: seawater, rocks, mayonnaise. And by seawater, I mean like gunky seawater, like seaweed in some places, dirt and mud. Pure substances, examples are water, salt, sugar, baking soda. So to separate pure substances even further, we have to ask ourselves the next question. Can the pure substance be further broken down by chemical means into simpler substances? If the answer is no on the left, then we have what are known as elements. So I'm going to put a box around elements there. Elements are on the periodic table. They cannot be broken down further without losing the identity. So we just have examples there for you: oxygen, carbon, gold, silver, elements of the periodic table. On the far right, chemical compounds are if you can break down the pure substance chemically. Regarding a chemical, you need a chemical reaction to do it. So examples are water, sugar, baking soda. All right, moving on. Next page of notes. It says, example, are the following mixtures or pure substances? A, concrete. B, helium in a balloon. C, lead weight. D, wood. Well, concrete is a mixture, right? It's not uniform throughout. Helium is a pure substance. It happens to be an element, which is a breakdown underneath pure substance. Lead weight is also pure substance. Of the pure substances, compound or element, it is also an element. And then wood is a mixture. If you get really close and look at wood closely, all the fibers and everything all look different. So it is a mixture. All right, example number 2 on this page. Chemical or physical change. A, separating a solid from a liquid by filtration. B, producing CO2 gas and solid lime by heating limestone. C, mixing alcohol and water. Well, a chemical change is something that's a little more severe, and a chemical change is kind of like a reaction, right? Physical changes are something that are often reversible, and you can put it all back together without really changing anything. So A, separating a solid from the liquid by filtration, physical change. B, producing CO2 gas and solid. This just sounds like a chemical reaction. B is a chemical change. Mixing alcohol and water, I could always separate them out in a variety of different ways. This is a physical change. Bottom of the page, star, chemical elements, symbols, and formulas. All right, so we're going to talk broadly about the periodic table now, and there's almost 120 or so elements on the periodic table nowadays. Some you know: oxygen, iron, gold. Some you've never even heard of, like rhenium, molybdenum, niobium, californium. There's some really weird ones. Now, the top of this page of notes, it starts out by saying there are 4 elements of those 120 or so elements on the periodic table. 4 elements are essential for life, and you've no doubt heard of these: CHON, carbon, hydrogen, oxygen, and nitrogen. All right. So the second bullet point there says all elements are represented by chemical symbols in the periodic table. Sometimes it's just one letter, sometimes it's two letters. If it's two letters, the first one is capitalized, second one is not. So chemical symbols made up of one or two letters, and the first letter is capitalized, second is not. All right. So yet another example problem. It says, what's the element's chemical symbol? And we'll use the periodic table. You should have one inside your textbook. You might have one. You can always find one on Google Images. So what's the element's chemical symbol? Use the periodic table. A, uranium is U. Titanium is Ti. Tungsten is W. You might be wondering why tungsten is W. The Latin name for tungsten is wolfram. Example, what elements do the following symbols represent? So now we're going to go the other way. We're given the symbols. What's the name? Well, Na, Ca, Pd, K, Sr, and Sn. Na is sodium, Ca is calcium, Pd is palladium, K is potassium, Sr, strontium, Sn is tin. All right, now more on atomic symbols, symbols on the periodic table. It says symbols which represent elements on the periodic table are combined to make chemical formulas. So a chemical formula is going to represent a chemical compound. So it said, what it's saying here is that you take a symbol on the periodic table and you combine it with another symbol on the periodic table, and you can make a chemical compound, and that chemical compound has what's known as a chemical formula. For example, if I take Ca, calcium, and O, oxygen, and I put it together and make CaO, that's calcium oxide. Calcium oxide is my chemical compound. CaO is the chemical formula. All right, so let's do an example. Which elements are in each formula, and how many are there of each? So really, you just have to have eyes to do this. So for NH3, there's one N and three H's. For B, NaHCO3, there's one Na, one H, one C, and three O's. C8H18, well, that's 8 carbons and 18 hydrogens, right? So what you're seeing there in A, B, C, D, and E, the first thing I'm writing, like NH3, NaHCO3, C8H18, and then E is CaBr2, those are chemical formulas, and they represent chemical compounds. All right, so further delving into the periodic table here, we're going to break it down into three main sections. We have number one are the metals. Metals are the most abundant type of element on the periodic table. These guys are malleable, which means you can hammer them into thin sheets. You can kind of flatten them out like aluminum foil. Ductile means it can be drawn or pulled into a fine wire. Lustrous means they're shiny. In general, metals conduct electricity. Most of them are solids, and they're found on the left-hand side of the staircase on the periodic table. So as far as the periodic table is concerned from a mental viewpoint, metals are in the middle and off to the left. And there's like 90 plus, more than 90 plus of the roughly 120 elements are metals. Most of the elements on the periodic table are metals. Number two, there are 17 of them, and they are nonmetals. Nonmetals are poor conductors of electricity, right? The opposite of metals. They're found on the right-hand side of the periodic table, kind of above the staircase. The staircase is where we're going to separate metals and nonmetals. So that staircase, what's separating metals from nonmetals, all the elements along that staircase are going to be the metalloids. And there are 7 of them, and you would want to know all 7 of these metalloids. These used to be called semi-metals back in the day. But as you might expect, metalloids being on that staircase, that the boundary between metals and nonmetals, metalloids share properties of both metals and nonmetals. As I've mentioned several times, but now we have it written down in our notes, it says, found in a staircase manner between metals and nonmetals on the periodic table. The metalloids are boron, silicon, germanium, arsenic, antimony, antimony is Sb, Te is tellurium, and At is astatine. All right, so that ends my chapter 1. My chapter 1 might be different than your textbook's chapter 1. That's fine. The assigned homework problems will be associated with my chapter 1, okay? So now we're on to my chapter 2. This is called Measurements in Chemistry. So a few things, excuse me, a few things to get through here before we move into some of the measurements in chemistry. I want to mention to you something called physical quantities. Physical quantities require both a number and a unit. For example, 15 grams, 34.3 meters. You have to have a unit for it to make sense. So whatever it is you're talking about, height, volume, mass, temperature, you can't just have the number there. In the example, you can't just have 34.3. It's meaningless. You have to have a unit behind it. In this example, 34.3 meters. A number alone would mean nothing. So any physical quantity can be measured in many different units. For example, I can measure a person's height in meters, in centimeters, in inches, in feet, etc., right? So any physical quantity can be measured in many different units. So to avoid confusion, scientists have agreed upon a set system of units that we all use globally. That way we can compare our lab results to each other. We can compare, like you don't want to do one set of lab results in one unit and then have everything else come out in yet a different unit. You want your stuff to match up so you can compare with other labs around the world. So we have something called SI units to take care of that. SI really is just International System of Units. The reason why it's SI is it was French, Système International, as opposed to in the United States or in English, International System. So SI units is just the International System of Units. And here they are. Mass, kilogram. Length, we use the meter. Volume, we use the cubic meter. Temperature, we use something called kelvins. And then time is seconds. So look at that. Mass, kilogram, length, meters. See all volume, cubic, meters. Those first three look like giant units, something you might not want in chemistry. We'll get to that. Now, as a side note over here, I'm writing down some notes on what are known as the metric system. The metric system is not the same as the SI units, but metric system are also heavily used, especially in chemistry. So for mass, we use grams, volume, liters. Temperature, we like to use Celsius. So please note the difference between those two. Now, as I mentioned, some of the units up there are huge, way out of range for something so tiny, tiny, tiny as like the diameter of an atom, right? So metric and SI units can be modified by prefixes to refer to smaller and then even larger quantities. Example, diameter of a red blood cell would be 0.0000006. I think I said too many zeros, but you get the idea. 0.00006 meters, or we could just say it's 6 micrometers. That little curvy U is a micro. Example, distance from Earth to the Sun, 150 gigameters, or 150 and then 9 zeros meters. So you can see that prefixes come in very handy for putting our units into proper physical quantity amounts. All right, so that's it for the first video of week number 1. You now have video 2 and video 3 that you're responsible for in week 1. All right, after you've seen all 3 videos, make sure you rewrite these notes in your own little notebook. That's how we retain information. You can watch the videos hundreds of times, or you can write the notes down on your own, maybe 1 or 2 times, and you'll get just as much retention, all right? Plus, these are the notes that you want to have in front of you, videos 1, video 2, and video 3, when doing the homework that's been assigned for week number 1. All right, so on to video number 2.